Q4 is the phase change in vaporization, and Q5 is the last delta T with 130. So go ahead and add or calculate them and add them up. As you're doing that, I'm just going to come around and look at your endo-exo work. The at-home investigation. After you get all your Q's, you have to add them together. Sorry. Do note, what were the units for Q in your MCAT ones? Huh? Your unit for Q in MCAT. Just joules, right? So joules for all the Q1, Q3, and Q5. What was it for the phase change ones? Kilojoules, right? So you got to convert either all of them to kilojoules and atom, or all of them to joules and atom. Don't add kilojoules to joules because those can't be added. It's like out of the capitalist oranges. So since delta HVAP is 40.7 kilojoules per mole, your Q is going to be in kilojoules when you get that. I cannot add this kilojoule to the joules that I get when I just do normal Qs with MCAT. So I've got to convert kilojoules to joules first. That's all. I'm just making sure you know you need to do. We have it added together. So tell me what you're getting here, because I need to go ahead and I need these values so I can show you the final. What's for Q1? What do we get? 1,626 joules. Q2. Okay, say it again. 27 joules. Q2.
17 point, well, I guess 18.
Just tell me your final answer.
They're in kilojoules.
Okay, give it to me in joules, so times by 1,000.
0.01764.
How many kilojoules did you get?
17.64.
So 17.64 kilojoules would be 1,000. Yeah, you went the wrong way. 1,000 joules over 1 kilojoule. So that would be 17,600 and what? Okay, I'll go with that. 69 joules. These are going to be, it's okay if it's slightly approximate. We're going to get a large number. Q3.
22,122.
Not 122?
122.2.
Okay. That's really large, but I guess that's a lot of water. Okay. That's cool. Q4?
Is it 117,897 kilojoules? That's not. I mean, not kilojoules, joules.
Joules.
I got 13,891.
Can I get a confirmation on Q4? Who else has done the phase change? Q4.
Oh, hold on. Yeah.
You took 52 point, what was it?
Isn't it moles?
52.9 mol or grams. 52.9 divided by 18.02 times 40.7
I got
times 1,000.
Oh, I used 40.1.
I got 1.19 times 10 to the 5th, so 1.19. I'm going to change that to a 9. Okay. Okay. And then the last one, Q5, is where the vapors were. Last one. 52.9 times 2.02 times 130. 13,891. Yes? Okay. Joules. All right. So as you can see, this is a process you have to go through. Once again, 5 Qs, 2 different types of equations, add them up, and you get your total QH. Or heat. Yeah. You have to do Q is equal to moles of water times the delta H of fusion here. And this one is moles times delta H of vaporization. For the moles, though, you have to convert to moles first. You have to take your 52.9 grams of water times 1 mole of water, which is 18 grams. So that divided by 18. And then multiply by the H of fusion for 6.01 kilojoules per mole. So it requires you to go to kilojoules and then times it by 1,000 to get it to same thing for this other one, except this is 40.7 kilojoules per mole. Okay, and so you have another one on there similar to this one, but I think it's going the opposite way. It's a cool curve, so it's going from gas to solid, and you have to figure out how much energy is released when it does that. And that's on the U-try part. Yeah.
On a test or quiz or whatever, are we going to have the
C values?
Yes.
Yes. I'll give you the C values and I'll give you the delta H's, but you have to know how to use them.
Oh, okay.
Yeah, I don't mind giving you like little constants because I had to go look up these C's for the other ones. I don't know those. Yeah. 40.1. I could have, or maybe I wrote a 7. It looked like a 1. I could have said it's 40.7. I'm sorry. So it's 40.7. It's 6.01. You know, my handwriting and stuff. Okay, so let's go back through and talk briefly about endothermic, exothermic, and then we're going to do our lab on specific heat. So how about your homework from last night, the at-home investigation real fast for me? And you probably want to write this part on the foldable, the last part that we haven't done. Just leave some space because we're going to do some thermochemical equations tomorrow. So I want you to have just the definitions right now. We know what endothermic and exothermic is. If you want to add just a brief note on that, that is fine. I'm not asking for much here. What I do want you to know is where to write it in the chemical equation and how does the delta H look whenever you see it. So if it's endothermic, you have a positive delta H. What does H mean again? That's what delta means with H. Enthalpy, yeah. These are going to be for the fourth lower right one that we've not done yet. Yeah, thermochemical equations. So just do a brief outline on this one because we're adding more to it tomorrow. So endothermic means you have a positive delta H. Exothermic means you have a negative delta H. Whenever you are writing it in the thermochemical equation, it's just a BCE. We just call it a thermochemical equation because it includes something about its thermochemistry. So for example, you'll either have A plus B plus energy yield C, something like that. Or instead of me showing you that energy is in the reactants, it'll be given to you as A plus B yields C, and then over here out to the side it'll say delta H is some positive number. So this is the way that you'll see it on your problem set. It'll say a thermochemical equation is blah blah blah, and then out to the side it'll say H plus is plus 60 kilojoules. So it's going to tell you it's endothermic by the positive number. So how is the exothermic one going to be written? And then so it'll be delta H is some negative number. Yeah. Or you can read it and you can say A plus B yields C plus energy. Because as you can see, if the energy is written in the products, then it's being released, and so that's an exothermic reaction. So which of these feels hot to the touch? Right, this one will feel warm to the touch. This one will feel cold to the touch because it's actually taking energy in and it's consuming it. It's using it. So it's taking away our kinetic energy, so we're left with a feeling of coldness. And whenever you're writing out your BCE like this is now a conversion factor. So for example, I can say that delta H to this number, let me write it up here. So like we've been writing 60.01 kilojoules per mole or 1 mole of water. So the number that I used here is for the heat of fusion of water, but for example, if this was like positive 100 kilojoules, that would be 100 kilojoules is used for every 1 mole of A. It's like a mole ratio almost. 100 kilojoules is used for every 1 mole of B. 100 kilojoules is used for the production of 1 mole of C. So I can actually use this in a question. So if I said something like, I'm just going to do this. If I said ammonia, let's do the Born-Haber process. Let's do nitrogen plus hydrogen yields ammonia. Balance that for me. So 3 here. Is that good? Okay. And I said that this was an endothermic reaction where you had a positive 30 kilojoules produced. All I'm going to say is if I supply 300 kilojoules of heat, so if I give you 300 kilojoules of heat, how many moles of NH3 can be produced? What's my starting point? 300 kilojoules, right? Okay, so I can start with 300 kilojoules of heat. So then the next part comes in, we have to use a conversion factor, right? Well, where's my conversion factor? It's not explicitly told to you, but it's telling you that you're going to need to use 30 kilojoules of heat to make 2 moles of ammonia. So this now is a conversion factor. 30 kilojoules of heat for every 2 moles of NH3 that's created. All I'm doing is just putting them together. So here, if I write it like this, I can't cancel kilojoules, right? So if I write it opposite, for every 30 kilojoules of heat used, I'm going to be able to make 2 moles of ammonia. So what's 300 divided by 30? 10 times 2? 20 moles of ammonia can be made using 300 kilojoules of heat. So a thermochemical equation has got some stoichiometry applications as well. We're going to do a lot more of these tomorrow. I just want to do the intro. It's a good example. Okie dokie? Okie dokie. And last thing these things that you drew last night are called reaction pathways. So that's one name of them. And if you want to just add that to your homework from last night, just the name of that, that's cool. Or you can call it coordinate diagram. And so it's going to tell you if a reaction is endothermic or exothermic just by simply looking at the graph. So if my products are higher in energy than my reactants, how do they get higher in energy? So energy was put into the reaction. So it's endothermic, right? So if you just think of it simply like that, you can actually tell if it's endo or exo basically by looking at a graph. How did the products get higher? Energy was added to that reaction. How much energy? Where is the difference in energy here? So between those green lines, right? So between the products and the level off area of the reactant. So this area here is called delta H. Is delta H positive or negative if it's endothermic? Yes, it's positive. Okay, so if you're adding to your endothermic graph, that's great. Thank you. What is this energy called? The energy it takes to get from the starting point of the reactant all the way up to the tippy top up here. I talked about yesterday, I said it was the energy that you need to start all the chemical reactions in your body. Not quite. Huh? It's called activation energy. EA, I called it EA. You need to write this down again if you need to. Activation energy. So this is the energy from the bottom of the reactants to the top of the curve. That's the energy that has to be applied for these products to actually get formed. If not, it travels all the way up that hill and it gets there and it's just like, oh man, I don't have enough energy, and it falls back down. The reaction would not occur unless that energy is supplied. So that's just called activation energy because that's the energy to activate that reaction. One more thing, the star up here, the very, very tippy top, is called the activated complex. So it's actually a chemical, so I've got reactant A and B, they're coming together, and then they hit, and they make this new hybrid. The hybrid is called the activated complex. And if it has enough energy, it's going to go and form C, and if it doesn't, it's going to stay up here and then fall back down to the reactants. So it's just a certain name for it. It's called the activated complex. But other than that, endothermic looks like it's a curve up a hill and then it stops kind of at the top. The other one is exothermic, and it looks like this. So I've got some labels here for you. Notice that the reactants are starting up high and the products are ending down low. Well, what happened to the energy between them? It went away. It got lost. It got put out. So that's exiting. So it's exothermic. How about this activation energy? So starting at the level of the reactants and going up to the tippy top. What do you know notice that's so different between this one and the last one?
Much smaller.
Much smaller. So which one's easier?
This one?
Right. So like here, you can have 3 kilojoules of heat or energy. The other one's going to need like 300 kilojoules because it was so high to get up there. So which ones are easier to occur? Endothermic reactions or exothermic reactions? Definitely exothermic are easier because it has a lower EA, a lower activation energy. That's a point to know. And then actually you can see it here, but the energy that's released is between the level of the reactants and the level of the products, which is represented by the 2 here. That delta H is negative or positive? Negative, because it's exiting, so the energy is exothermic. Or the reaction is exothermic. Alrighty? Alright, so if you can label those and draw them and relate and know it next to it, then you're good. Let me show you what we're going to do for our lab, and then we'll come back together at the end of class and just conclude together. I'll have to do my demo for you in a second. Okay, so the specific heat of a metal lab is what you're doing. You're going to have a metal and it has a number on it. Write that number down right when you get your metal. Because you're going to confirm with me later, so I can tell you what the specific heat is. So you're going to have to use the coffee calorimeter. It's literally a styrofoam coffee cup. We're already using a coffee cup. What you're going to do is you're going to heat up water on a hot plate. Not for this long hot plate. Milk. Okay. Styrofoam cup will milk. Heat it up with a beaker. Have your thermometer. No, thermometer. Some of them can be little gaps here and there. 3 thermometers. And you turn around. These little gaps. thermometers are cheap. These do not like shove the thermometer in the bottom to make a hole. They have to have the lid on it when you're trying to capture all your energy. The lids are extremely expensive and accurate. So you're just gonna have to make it work. And I have some other lids that I can try to give you. They've been loved, well loved. Okay, so if you have to put your thermometer through a little hole in the coffee cup here, not through the sippy part, because that's too big of a hole, and your heat will escape. Heat escapes very easily, so if you have a high percent error, like a couple hundred, like 400% error, don't be alarmed, it happens, because the heat is so hard to capture. So we'll have to try our best to account for that heat, and then look at our C's that we calculate in the lab, and compare them to the C's the specific heat list on the board. That's how you'll do a percent error. And a lot of people got percent error wrong for like one group on our last lab. How do you calculate percent error? A minus E over A times 100. What is A over E times 100? Or E over A, I don't know what we were doing. What does this look like? That's percent yield. Percent yield is not percent error. This is percent error, it's the difference. Yield is actual yield over theoretical yield times 100. So we're not doing yield, we're doing error. Alrighty? The lab is called specific heat of a metal. Honors chemistry, specific heat of a metal. Take about 45 minutes.
K10, 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 minor group. That's enough, right?
Specific heat of a metal, and I might have them with me. Guys, I have the copies of the lab. My bad. I'll give these to you right now. I don't know. I thought they were in the lab.